Thank you very much. So welcome everyone. This is building a DIY baseband debugger from scratch, and my name is Eneko Cruz Elejalde. I am a researcher for Exodus Intelligence, and my main interest is vulnerability research and exploit development. But although we do have a mobile team at Exodus Intelligence, this is my own personal research, and this is unrelated to anything that we do at XI. On this presentation, we're going to go really quickly through a very, very brief introduction to baseband. We're going to go through what we actually need to get started in baseband research. We're going to take a look at how we are going to build a baseband debugger for targeting the HTC-1 M9+. And finally, to demonstrate this, hopefully the demo code starts smiling to me, we're going to be setting a breakpoint, reading a GSM message from memory life. So as a really brief introduction to baseband, we need to take into account that a smartphone is very different from a computer. In a general purpose computer, we have a single processor, a CPU, running everything, and some peripherals. Whereas in a smartphone, we have multiple processors, an application processor, digital signal processors, Wi-Fi chips, and the baseband processor that are working together to achieve a common goal. In case of the baseband processor and the application processor in a smartphone, they do communicate using shared memory interfaces, as well as in case of the application processor and baseband processor case, they use AT commands. So all in all, at the very minimum, a smartphone is going to be running a Linux kernel, an Android operating system, some user applications, and a firmware for each processor. The application processor is going to be running a Linux kernel and an Android operating system and any user application that you can think about, whereas the baseband processor is going to be an ARM chip in this case of this particular phone, running its own operating system or firmware. As you probably know, the baseband processor is the one handling cellular communications with cell phone towers. Why is this interesting to us? Why is this interesting to me particularly? Because this is a pretty old code base and it's actually written in C and C++, which, as you might know, this can bring a lot of bugs. In this case, for the HTC-1 M9, I found that in the baseband there is no privileges separation whatsoever in the baseband OS. But however, the entry bar is higher, as you do need some hardware. And this actually means that there is less research available on the topic. On top of that, most interestingly, this offers the possibility of triggering remote code execution over the air without any user interaction whatsoever. So, as a bare minimum to get started in baseband research, we do need a phone. We need some a cellular setup, which is comprised of a hardware setup and a software setup. And we need also as a minimum to have access to the baseband firmware or the OS binary. It's also very nice to get some debugging symbols, as always, and it's also very nice to have a debugger. Building the debugger is the main topic for this talk. I'm going to be targeting the HTC-1 M9+ today. It is a pretty old baseband. It's from 2015, but it's actually very great. It's a really good platform to get started. These go for around $100 on eBay, and so far I've destroyed 3 of them in my test. The pros of using this platform is that routing is partially supported by the manufacturer, and most importantly, the baseband firmware is not signed or checked whatsoever. For this research to be extended to other platforms, the baseband firmware not to be checked is a requirement, and routing the phone is usually a requirement also to be able to override the baseband firmware. Inside my target, I have placed a SIM card. Not just any SIM card, is one of which the IMSI is known. These are manufactured by Sysmocom. The IMSI, the International Mobile Subscriber Identity, is going to be known to OpenBTS, and therefore this phone, when the SIM card is inserted, is going to be allowed in the network. Although others should work as well. So far, I haven't found a single SIM card that didn't work. The cellular setup, which I have right here, looks like this. This is a tabletop device, and what the box is actually an earth enclosure, which is going to prevent radio frequency from escaping and is going to prevent interfering with legitimate cellular communications. Inside it, I have a Dell machine. The power supply unit had to be stripped because I could only drive up to 50 volts inside the RF enclosure. So I had to take the power supply unit off the Dell machine and put it outside, driving just a few cables inside. There's also a USRP B200, which is an SDR device, a software-defined radio peripheral, and right next to it, there's the target phone. Under the phone, there is a fan because inside here, it gets pretty hot, especially when it runs for a prolonged time, so it does need to be cooled down. And this is what it looks like in very abstract terms. So this Dell machine is running Ubuntu 12.04 and is running OpenBTS. OpenBTS is going to be the base station software. OpenBTS is directly controlling our USRP, and we are also controlling the test phone through ADB. The USRP and the test phone are obviously going to be talking using over GSM, and this all is going to be controlled by another machine that is sitting outside of the RF enclosure, and is going to be communicating over serial connection. The reason to use a serial connection instead of anything else is that this RF enclosure is really good at something. This is isolating radio frequency, and therefore I could not drive an Ethernet connection through it because there are capacitors separating the inside and the outside, so the signal would get too attenuated. So right now we are done with cellular setup, and let's take a look at how we can actually find the firmware and or the OS binary for this box. It turns to be stored in the file system. It's really easy to fetch it, and this image is designed to load at position 0 in the baseband processor memory, and as such, because there's no encryption or whatever, it can be directly loaded into IDAPRO. It is some reverse engineering showed that it's actually based on Nucleus Plus, which, as you might know, is a real-time preemptive operating system. It is written in C, and there's quite a lot of documentation available online, so it's really easy to reverse engineer what MediaTek built into this. The source code also turns out to be partially available online for unknown reasons, so that is even better. Now that we have the baseband firmware and the OS binary, we are going to take a look at how we can find debugging symbols. This can also be found in the file system. It's really easy to find them, and they're directly loadable into IDAPRO with the script that the guys at Comsecuris developed. And by the way, the rest of this research builds upon Path of Least Resistance by Comsecuris, which is an excellent piece of research and a really good point to get started. So now that we have this really brief introduction to baseband and how we're going to start with it, we're going to get to the debugger. We want to build a debugger, and we want to be able to do these things. We want to be able to read memory. We want to be able to read registers, write memory, add breakpoints, and after adding breakpoints, we also want to be able to remove them. So to do this, we need to take the following steps. So we first need to choose how we're going to get the baseband processor and the application processor to communicate. And for this, we have multiple options. We can choose between AT commands and shared memory interfaces. AT commands, as you might probably know, make use of the serial interface between the baseband processor and the application processor. Therefore, are synchronous, and they're quite well documented, meaning that there are lengthy PDFs documenting the AT command set supported by the baseband chip in question. There's also shared memory, which is pretty undocumented, and it's used primarily by the radio interface layer daemon. So we're not going to go for shared memory, we're going to go for AT commands, and our strategy is going to be to find an AT command that is not used and overwrite this command handler with some sort of debugging stuff, debugger stuff that we're going to be building. To send AT commands on a MediaTek phone, I found out that there's /dev/ttic0, which is the serial interface between the baseband processor and the application processor. However, the GSM multiplexer daemon is permanently attached, which makes it useless. However, the multiplexer daemon exposes /dev/radio/atcy1, which stands for AT command interface 1. We can just echo our AT commands to it. But of course, as you might have guessed, there are better solutions. If we take a look at logcat while we are issuing our AT commands, it turns out that the radio interface layer daemon writes unsolicited input, unsolicited AT command output directly to logcat, so we can either grep it, or even better, we can install a ptrace hook into the radio interface layer daemon to patch a single call to this Android log buff print to intercept whatever was meant to be written into logcat. Now that we have chosen how we are going to communicate how the communication between the application processor and the baseband processor are going to take place, we need to choose a debugging mode, and we need to decide between paradigms. We have to decide between halting mode and monitor mode. If we're debugging in halting mode, the CPU, the processor in question, is going to be stopped completely while we're debugging a task. And if we choose to debug it in monitor mode, the CPU is going to maintain functionality. We have different constraints here. As I already mentioned, Nucleus Plus is a real-time operating system, and it has a number of tasks running. These tasks need to continue running as long as the baseband is working, because otherwise we would be interrupting baseband and we would be interrupting cellular communication. We really don't want that. And on top of that, the communication between the application processor and the baseband processor, as we decide, is going to be done with AT commands, and therefore we do need the baseband to cooperate with us. Therefore, I ended up choosing monitor mode, but this is not going to be very important until we're dealing with breakpoints. So now that we have made some key decisions, we are going to first try to patch this firmware to pass a string from the baseband processor to the application processor. We chose the ATI command, and I found out that the handler for this AT command is in the function RMMI ATA handler, which permanently sits in this address, as there is no ASLR whatsoever. The RMMI AT handler function looks like this. There are two interesting function calls right here: RMMI fast string print, which is similar to printf, and RMMI write to UART. What is happening here is that some information about the baseband is being grabbed, is being passed to RMMI fast string print, and finally RMMI write to UART. And RMMI write to UART does exactly what you think it does. It sends some string over the serial connection to the application processor. So our strategy right here is going to be to make some room in this stack in the patch that we're going to develop, and we're going to be calling RMMI write to UART to pass a custom string, whatever we want, back to the baseband, back to the application processor. The string that I chose is going to be hola, which means hello in Spanish, by the way. So here we're making some room in this stack. We're configuring R0, R1, and R2 with arguments, and we're just loading the address of RMMI write to UART into R6, and we're just calling it. Pretty simple so far, and the next step, knowing that we can just send data, we are going to figure out if we can pass an actual datum, an actual hexadecimal value, and an integer from the baseband processor to the application processor. In this case, we're going to try to read a single register, for example. So the strategy here is going to be to make some room in this stack once again. And instead of calling RMMI write to UART directly, we're going to first call sprintf, passing a format specifier that consists of %x 0000 to convert this datum into a string. This is first CRC programming. And I did observe that if the datum's first byte is 00, there's a crash. Rather than looking into the root cause for this, I decided to work around it, and I did this by checking whether or not the datum's most significant byte is set to 00 and apply a different format specifier whether it is or not. Finally, we call RMMI-WriteToUArt to return this string to the application processor, and this is what the patch looks like. If this is the mystery argument that we want to send, we're just going to load it. We're just going to call sprintf to create a string in the stack right here at sp plus 0x4, where this is going to be where our return string is going to be placed. We're going to call sprintf right here, and with the result string, we're going to call RMMI-WriteToUArt again, passing the string that we just created. This is really simple, and by the way, this is going to be what it would look like graphically in the baseband memory. So as you can see, this is what we overwrote, and this is going to be our patch. And as you can see, it is returning prematurely without executing the rest of what we did not patch. Now that we can patch the firmware to pass data from the baseband processor, let's see if we can do the opposite. Let's see if we can pass some data from the application processor to the baseband processor. And fortunately, thanks to the previous patch, I observed that it is now possible to read registers, and I did observe that R1 contains a pointer to the AT command pass. To the AT command passes the string that represents the AT command that we just passed. So it is really simple. Once again, we can call atoy to parse the decimal string that follows the string ATI. So after ATI, there would be a number, and we can just call atoy on that number following the string ATI. We can call sprintf once again, and if we call RMMI-WriteToUArt, we can get the baseband to echo whatever we just sent to it. However, we're just one instruction away from being able to read the whole baseband memory, as with this integer that we just managed to pass to the baseband, we can index memory. So if we use the parse integer, parsed by atoy, to index memory, we can just read whatever there's in the baseband. Here I'm fetching the AT command string, which is now going to be pointed to by R0. I am calling atoy right here. I am then applying a different format specifier, depending on whether the most significant byte is set to 00 or not. I'm going to call sprintf once again, and I send back whatever came out of sprintf back to the application processor. We can now read the whole baseband memory. However, writing memory is a different business. We will have to disable some memory protections, and these memory protections come in two different flavors. They're memory protections set by the baseband processor firmware on its own memory, and the strategy is going to be to deal with this by patching the firmware once again. There are also memory protections set by the application processor in startup, and to undo this, we are going to load a kernel object into the host kernel to undo basically what the kernel did to us on baseband processor startup. It turns out that the baseband firmware sets its own MPU at the function MPU_init. And this is done by several calls to MPU automake region and MPU make region, which if we reverse engineer them, it turns out that they are actually programming the MPU programming registers. I reverse engineer these calls, and it turns out that there are 9 of them, and these are the memory regions that are defined with the respective protection flags. We specifically we have issues with region number 6, region number 7, and region number 8. So to undo them, we are going to overwrite the instruction setting the protection flags into the R2 register, which is later going to be used to program MPU registers. We're just going to override it with an instruction that sets a different value in R2. So to deal with regions 6 and 7, we're just going to relax we're going to configure R2 with a different protection flag that is going to just disable the write protection. And the same applies for region number 8. Now that we have disabled the baseband processor memory protection, I was trying to write memory after I had disabled this, but it was for some reason impossible. And I did notice on the message during the baseband processor restart that this was being logged. This led me to believe that the kernel is setting up some memory restrictions, and it turns out that this is the case. The partial source code for responsible for loading up the firmware and starting the baseband processor is available in GitHub for unknown reasons, and it turns out that indeed there are two regions being flagged as read-only or forbidden completely. And to deal with this, we can just create our own kernel object, and we can call EMI MPU set region protection to undo these protections. Here you can see that we are programming no protection for both regions that we are interested in. Now that we have disabled our memory protections for the baseband completely, we can pretty much write memory. We can write wherever we want in the ROM. We can actually instruct the baseband processor to write wherever we want in its ROM. And if we want to write to executable memory, if we are going to write instructions, instruction barriers do become important at this point. To our final goal of building a debugger, I decided to define two new special memory areas that are going to be shared between the debugging task and the debugger task, which are going to be the debugger status block and the write register bank. So both the debugger status block and the write register bank are shared between the debugger and the debuggee, and the debugger status block is going to be a set of flags set up by the debugger for the debuggee to act upon. These flags are going to be dump all registers or remove the breakpoint or whatever. Whereas the write register bank is going to be basically a snapshot of all the registers created by the debuggee for the debugger to consume and send back to the application processor. And now for the real deal. Now the most important, most difficult thing, we want to set some breakpoints. So we are going to consider that when we're debugging a baseband, we are going to have two tasks at any point. First, the debugger task is going to be the AT command handler that we just overwrote, and it's going to influence the debugger task. This is going to be doing it in two ways. First off, it's going to be setting flags in the debugger status block for the debugger task to act upon, and most importantly, it's going to replace any instruction that is going to hopefully be executed by the debugger task with a breakpoint. The debugger task is going to be any other, and is going to be stuck in an active wait loop when a breakpoint is encountered. In this loop, it is going to want to read the flags set by the debugger and act appropriately on them. So, for example, if the debugger instructed the debugger to dump its registers, it's going to do so, and if the debugger instructs the debugger to replace its own trap instruction on breakpoint removal, is also going to do so. The breakpoint instruction that we are using is software interrupt, SWI, also known as SVC, and it's kind of similar to the x86 or x64 int instruction. And when executed, the processor operating mode is going to become supervisor, or SVC, and execution is going to be resumed at the address fetched from the interrupt vector table corresponding to the SVC handler. In memory, it's going to look like this. So if this is our debugger task, when it hits a breakpoint, it's going to be stuck in a loop, and it's going to be querying the debugger status block that is going to be set by the debugger for actions to take, for instructions, and it's going to fulfill those by writing back into the write register bank, or is going to fulfill them by by removing its own breakpoint if instructed. After the loop is finished, when the breakpoint is finally removed, it's going to want to jump back to the original breakpoint instruction that will now have to be replaced by the original instruction. We need to take into account that in ARM we have two instruction sets. These are ARM and thumb, and the instruction set in use is always given by the bit T of the current processor status register. To alternate between these two instruction encodings, the branch instruction BX, and I think most of the branch instructions are going to copy the bit 0 of the PC, of the program counter, to the current processor status register. So for example, if we're jumping from an odd address to an even address, the instruction set in use changes from thumb to ARM, and vice versa. There are some challenges with the proposed architecture, namely that the breakpoint, the loop representing the breakpoint must contemplate whether originally the processor was executing thumb or ARM code. And finally, after exiting the debugging loop, the original processor mode has to be restored. Meaning that if this processor was in system mode, if it was executing a higher privilege level, it must go back into that original mode. Apart from obviously restoring registers, so as not to disturb the execution of the original program. On top of that, if we're running our task indefinitely in an endless loop, this is going to result in an starvation scenario, which eventually results in a baseband crash, so we need to avoid this somehow. To prevent starvation, I had to reverse engineer the tasks running in Nucleus Plus in this MediaTek baseband firmware, and I found that there are 60 tasks of them. The way it works is that lower priority tasks cannot preempt higher priority. So if there's a high priority task running, it cannot be kicked out by a lower priority task. And the issue right here is that our debugging task might have a higher priority than the debugger task. Therefore, if the debugging task is stuck in an endless loop, in an active wait loop, we might not be able to kick it out, as the scheduler will keep scheduling it without possibility to breaking the loop. Our options to solve this here are to set the debugging task to the lowest priority possible, but this gives way to many other challenges. And also on top of that, the correct workings of Nucleus Plus might depend on the priorities being configured correctly. So the solution in this case is going to be to force the debugging task to sleep in a way to force preemption. And we're going to do this by calling call sleep task, which takes a millisecond value. And the way this works is when call sleep task is called, then TCC task sleep is called, which does some error checking. If no errors are encountered, then TCC called task sleep is called. And finally, TCC task sleep calls TCC suspend task veneer, which effectively suspends the calling task for a given number of milliseconds. The issue, once again, is that call sleep task cannot be called into SVC mode. And we know that every time that the software interrupt instruction, that our interrupting instruction is executed, the processor is going to switch to SVC mode. So the solution in this case is going to be, on each iteration of the debugger loop, we're going to change to the original execution mode. We're going to call sleep task, and we're going to then try to jump back to the original breakpoint address. So if the breakpoint hasn't yet been removed, then SWI is executed again. We go back into the loop, and we execute everything over and over and over. However, if the breakpoint had been removed, the original instruction gets executed, and we continue normally in sequence. So our strategy for setting a breakpoint is going to be this. We're going to override the SWI handler address with the address of a function that we have patched into the firmware, and our breakpoint entry after SWI the instruction set in use is going to be ARM. So we're going to continue executing whatever we want into ARM. And we're going to use this opportunity to check the debugger status block to see what the debugger requested from the debuggee. And we're going to fulfill those. So if the debugger wants us to remove our own breakpoint, we're going to remove it here. If the debugger wants us to dump the registers, we're going to do it here. We're going to attempt to exit the breakpoint. And we're going to take a look at how we exit the breakpoint a bit later. However, if the debugger had instructed the debuggee to remove its own breakpoint, we're going to patch again the breakpoint instruction with whatever was there originally. And when we are attempting to exit the breakpoint, we are going to restore the operating mode of the processor as well as the registers. If this was ARM, we're going to before we jump back to the breakpoint address, we're going to call call_sleep task, and if we were executing ARM, we're going to just jump to the breakpoint address, which should be given by the link register. If it was thumbed, we just need to increment the breakpoint address by 1, which we just took from LR, from the link register, and we're going to just jump to the incremented link register, which is basically going to bring back the processor into thumb mode. The patch is going to look like this. So the way it works is that when a breakpoint is hit, the address of our modified SVC handler routine is going to be fetched from the interrupt vector table, and we're going to jump to it. We are going to do whatever the debugger instructed us to do, and we're going to do whatever the debugger instructed us to do by checking the contents of the debugger status block and by updating it if necessary. Once we're done with this, we're going to try to jump back in a way that we are reattempting the instruction that triggered the breakpoint after we have called call_sleep task. And now, for my greatest trick, I'm going to try to set a breakpoint, and in a live baseband target, I'm going to try to read a message from memory live after sending a GSM layer 3 message. There are two important scripts that we need to be familiar with, namely debug agent new.py, which is going to be controlling the debugger via ADB, via the Android debug bridge. Basically, the debugger agent is going to be issuing the AT commands that corresponds to the actions that I want the debuggee to take, instead of me having to craft them manually. Final.py is a script that we're going to be using to deliver a base64 encoded GSM layer 3 message directly to the baseband. Because we're using OpenBTS here, OpenBTS allows us to open up a test call, which results in the opening of a UDP socket in the local machine, to which whatever we send is going to end up being delivered to the layer 3 of the GSM protocol stack in the baseband. So this script actually understands most of GSM layer 3 messages, thanks to this, which is a spreadsheet that I created by dumping most of the PDF GSM specification messages right here, and then parsing it using Scapy. The final.py script is also going to manage OpenBTS startup if we require it to do so. It's going to check the association of the phone to our malicious base station, and it's going to do this optionally by means of by emulating taps and taking screenshots. And right before the test case is sent, we're going to ping the baseband over an AT command. We're going to issue the command AT, to which we expect to get an OK response. And finally, we are going to send this user message over the layer 3 channel, over the test call. We are going to be setting a breakpoint at this address. And we're going to send this test case, which is encoded in base64, which corresponds to a mobility management location update reject. We're going to be reading the registers on the baseband, so on the baseband chip live using the debugger, and we're going to be reading the memory live using the debugger as well. The test case is this one. As I told you, it's a location update reject. The reason why I chose this message is because we have this reject cause field right there, and it is I can use it to stick in there whatever I want. I decided to stick in there as the reject cause 4 A's, which are given by these 441 bytes right there. And because I am interested in verifying that this debugger works, I'm going to be taking a look at this incoming ILM struct, which is a variable passed to this L3 module by the lower layer. And I'm going to be interested in the peer-buff-ptr member, which should contain a pointer to the message that was just received over the air. Because I'm interested in this peer-buff-ptr member, I'm going to be interested in the contents of R7, which is written to right there. And therefore, I'm going to be overriding that call to mmcom has-off with software interrupt, which is going to result into the breakpoint getting hit, the address of the overwritten handler being fetched from the interrupt vector table is going to result in the debugger checking what it needs to do as instructed from the debugger, and as a result of this breakpoint being hit, execution is going to be stuck in this SWI instruction for a while. How long? For as long as we want to, given that all other tasks are going to continue normally. So let's get right through it. I already talked about what I have here. So right now there is no GSM network started. So I'm going to connect through my serial connection to the Dell machine inside the RF enclosure, and let's see what happens. So I'm using Tmax, which is a terminal multiplexer, and this is necessary because I only have one terminal. This is not an SSH link, this is just a serial link. So I can just get one terminal, and I need a terminal multiplexer. I'm going to go to tab 1, which should, I'm going to instruct OpenBTS to start. Now I need to close the lid, as right now there's a GSM network in here, and I don't want your phones connecting to it. Now that OpenBTS has been started, we can go ahead and install our ptrace hook. We can just clear this, start ADB. We need to figure out which process the MediaTek radio interface layer daemon is going to be running on, so that we can inject our ptrace hook on it. So we are attaching to each of the threads that this process is comprised of, and now that we have installed our ptrace hook, we can send and receive AT commands directly instead of having an undesired output being placed on logcat. Now that I have the ptrace hook running, I can just go to OpenBT. I can just go to my final.py task. Oh, actually no. So I'm going to reboot the phone for a second, and when it reboots, I'm going to manually associate it to this GSM network that I have created. Now it is booting up. And after this, even if the demo works, I'm going to show you a video of what it looks from the inside, because this shows it much, much better than using it from there. It's almost booted, so now I'm just going to associate it manually to the GSM network. So right now I'm searching for networks, which should show only one, the one that exists inside. And indeed it does show it. I'm going to click on it. And it's attempting to register it. Now I'm registered, so now I'm going to install the ptrace hook once again. So now we're attached to it, and we're going to get our test case. Now, file.py is loading the predefined message types. It's also going to make a few checks on whether the baseband is associated to our network. Now let's see what those checks look like. So right now a test call has been established, so we have a UDP socket that we can use to send messages directly to the GSM layer 3 of the target baseband. The test case is now ready to be sent, but right before we send it, we're going to use the debugger to set a breakpoint. And we want to set the breakpoint. We're going to first request reading the registers. This worked. And we're going to set a thumb breakpoint at this address, which corresponds to what I just showed before. So the breakpoint is set, and now we can just go ahead and send our test case. We press enter right here, and if everything worked, the debugger should be able to show us the registers at the time the breakpoint was set. Let's take a look at them. And indeed it worked. We were able to read the registers at the moment the breakpoint was hit. At this point, we're quite interested, as I said, in R7, which is going to contain the message that was received over the air. So let's read memory at that place. And indeed, as you can see there, effectively, the whole message that we intended to send, including the 4 A's, have been placed in memory as we could just read it. Hopefully the baseband hasn't crashed, so we are going to remove the breakpoints, and we're going to check whether or not, after execution continues, we are able to ping the baseband again over the air. So the breakpoint has been removed, and we can instruct file.py to carry on with other checks. Let's take a look at window number 5, and let's take a look at what happened. And indeed, we were able to pick the baseband over the air again, and we were able to also check that the baseband is indeed responding over an AT command, and the phone is still alive. It's still responding over ATP. And finally, I'm going to go back to the debugger, and I'm going to check that the baseband chip is still alive. And it's still alive, indeed. So the baseband processor didn't crash as a result of we debugging it. So I would say that this is successful at this point. Now I'm going to show the demo that I had pre-recorded, which shows the manual association of the phone. I'm starting OpenBTS once again. This you already saw. Now there's a GSM network inside the RF enclosure, and we're going to proceed to the phone to associate it manually to our network. We need to search for networks. We click on network operators. We search on networks. We search for networks, and right here is searching. If you were really sharp at this point, you have seen that at the top of the phone in the status bar, there are 3 bars representing that we're already connected to a network, but we're just going to search for them anyways. We see that indeed one network is found, so we click on it to associate, and we're registering it. Now that we're registering it, we can go back to the terminal and install our pretrace hook. And this pretrace hook, as I already explained, is going to allow us to intercept unwanted AT command results directly from the MediaTek radio interface layer daemon before they go to logcat. This you already saw, so now we're going to send the test case. We're going to prepare to send it. And here there are some checks being done on the phone to ensure that before we try to open a test call, the phone is associated to our cellular network, and the test call itself is stable. Now the test case is ready to be sent once again, and we send it by pressing enter. We request the registers to be read by configuring the debugger status block, and we set the breakpoint. Now, when the message that we're going to be sending is received in the baseband side, execution is going to be stuck. And we can read the registers once again. this is what I showed before already. We're interested in R7, so we can read memory at that point. And this you already saw, and we indeed we were able to retrieve the contents of memory at that point. So back to the presentation. I think this next slide we don't need because you already saw that the expected results are actually there. And by overwriting this SWI interrupt handler, we were able to indeed set and remove breakpoints. So our DIY baseband debugger wishlist is now complete. And of course, I'm going to be releasing this code later today, which is going to be comprised of all the firmware patches, the logic to patch the firmware image itself, the ptrace hook program, and the debugger agent. Oh, what happened? OK. And the debugger agent, or all of this is going to be later today in this address. So yeah, just go for it. And if you have some questions at this point, and if I can answer them, I would be more than happy to do so.